Okay, so welcome everyone for this week's ISyE Analytics seminar. Uh, I'm uh, I'm honored to introduce today's speaker, Dr. Radhika Kulkarni, who has recently retired as the Vice President of Advanced Analytics R&D at SAS Institute after, I believe, from my conversation with her, like after more than 30 years of service. So during her tenure there, she was responsible for the world's leading analytics software products portfolio. And moreover, she spearheaded the creation of the OR AI ML Center of Excellence, where they provided expert consulting to several Fortune 100 companies. Moreover, she has sponsored several partnerships with the universities and internship programs for PhD students and serves on many academic advisory boards. Most importantly, so Dr. Kulkarni is an Informs Fellow and Women in ORMS Award winner, and she has contributed in numerous ways to advance the career of analytics professionals. Today, she will be talking to us about machine learning, artificial intelligence, and optimization, opportunities for interdisciplinary collaboration. Dr. Kulkarni, thank you again for accepting our invitation. Please, whenever you're ready.
Okay. Thank you very much, Krish, for this opportunity, for inviting me, and to the department for hosting me virtually for this seminar. I'm very honored to be able to talk to you about some of my experiences leading the analytics R&D at SAS, where there were a lot of things which really excited me, and I was extremely passionate about interdisciplinary collaboration that we were able to achieve. So one of the things for my vision for leading the group was that it's all these different areas that form analytics, like data mining, forecasting, optimization, machine learning, tech support, text analytics, etc. All of these work better if people work together and try to find how they can use one technique within another and improve and provide innovation. So that was one of the main visions I had for the team. And I was lucky enough that our founder, the CEO, recognized that optimization was a key ingredient or a key factor in innovation in many of these techniques. So he invested quite a bit in optimization, which was good for me because I have an OR background, and that was one of my goals, to make sure that optimization was recognized. So over my career, we were able to use optimization techniques in many different areas. As the business needs increased, as distributed computing became more necessary, actually, then some of these techniques became even more critical. So what I hope to do today is to share with you some of my experiences, giving you some examples. And so my talk today will will focus a little bit, give you some idea of the business problems that are driving the need for speed, then opportunities that they created for innovation. And wherever there were examples of interdisciplinary research, I will highlight those as well. But at the end of the day, something that you recognize when you work with customers in real life implementation is that the most advanced and super efficient algorithm is probably not enough for success. In fact, it's not enough for success. There are many more things that are necessary to succeed in a project or an organization. And so I'll talk about some of the barriers to implementation and success. So the complex world of big data, the thing I'd like you to take away from this slide is that data is coming at us from all kinds of sources. It's from your cell phone, from all the sensors that we have in every machine that we use, all the complex machinery that we have, from Twitter, Facebook, LinkedIn, everywhere, and vision data, audio-visual files, audio files, all of this, they're coming at all speeds and at you from different directions. So how do you make sense of that, and what are the challenges? Some of the main challenges, I think, are in the fact that the data can come in many different forms, and the different disciplines that I mentioned, whether it be data mining, predictive analytics, forecasting, they all require the data to go into the model in different forms. Like for instance, if you're talking about predictive models to say who is going to respond to my particular campaign, you have an orthogonal data where you have observational data where every record refers to a different member with different characteristics, and you're trying to figure out what's the best offer to make to whom. So that is a rectangular data set. When you're looking at forecasting problems, you're looking at what will the future demand look like. So there's a time series involved. So when you want to look at how things have moved system-wide through the decades or through the time horizon, it's a combination of observational data and time data. So we call that panel data. So some of the algorithms might require your data to be in that form, or they might have the data in that. Then there is text data, network data, audio data, visual data. So you get the picture. There's data coming in all different sources. They are varied in many different ways. So the question then becomes, how do you get the best of all this? What do you need to succeed in trying to implement any system which is trying to use these different techniques? So first and foremost, you do need a platform that's able to solve all these problems, provide algorithms and models that you can implement, and then put them together. So I'll come to some examples later on. But anyone who has worked with big data or looked at public articles or common articles, you hear about the 3 V's: the volume, velocity, variety, veracity. There's a whole bunch of things that you hear about. But I claim that it's not just the volume, it's not how big the data are or how many bits and bytes you have, but it's the variety of data and your ability to handle the variety of data. That's where you get the biggest opportunities for insight. So I'll provide a link to these slides to Professor Iyer, so that you'll have the ability to look at some of these links that I sent you. So there was an article which talked about the different proportion where the insights were most valuable, whether it was because of variety, volume, or velocity. And you see that almost 70% of the value came from the variety of data. And some of the examples are, you may have legacy data sources that have been sitting around and you're building a predictive model, but then somebody comes and says, hey, here are some additional information that I have that sits in this particular source, in that particular source. How can I bring it all together and put them together to be able to get more value from your analysis? So also now with all the social media and other data sources that are available to you, you can augment your information for predictive models by taking information like, what do you hear on Twitter about a particular trend? What do you hear on Facebook about a particular trend? Or LinkedIn, what's been trending most popularly? So incorporating unstructured data, that was one of the things that many companies realized maybe 7 or 8 or even 10 years ago, that for instance, in warranty claims, when people were analyzing breakdowns of vehicles and trying to figure out what is the source of the breakdown, they used to use data which were numeric information about, what kind of part of the car broke down, how long was it in service, etc., etc. But then there was a lot of information that was left untapped, which would be just notes that the mechanic took down when somebody called and said, oh, here is the noise I was hearing, and tuck, 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 tuck noise or something like that. They've all captured that, but that doesn't get incorporated into your analysis. So that's when they realized that if I had abilities to mine the text data that are associated with it, maybe I can get more insight from it. And so incorporating unstructured data, which includes text, audio, visual files, etc. Network data is also something that's very, very valuable in building predictive models. So again, going back to the example of trying to give the right offer to the right customer, You again had information about, what kind of service they had, what kind of telephones they might have had, and so on and so forth. But then if you also had information about who their friends circle are, who did they know, how did they network, who's the one who has the most friends on Facebook, let's say. So what if we give him an offer for the latest and greatest iPhone or Android phone, and he's able to talk about it, then there are more people who will try and buy that, right? So this is the type of insight I'm talking about when I say incorporating data that are not the primary source for your analysis, but being able to take all of that information and incorporate it to get better insight. So that's the kind of thing I'm referring to here. Specifically, network information was something that I was very, very excited about, because one of the people in my OR group, he was actually very, very interested in doing graphs and network analysis, and doing a lot of cool algorithms for finding community detection, the connectedness, and all of that. And it was work that he was carrying out on his own. That was the same time when we started investing in social media analytics, or trying to figure out how can we capitalize on social media information and incorporating text analytics as well. So that became very, very important. And some of the applications we used were for fraud detection, terrorist network detection, targeted campaigning, for instance, who do you campaign to, etc. Then more recently, of course, as the current COVID crisis has been increasing, we hear a lot about contact tracing and figuring out what are the best ways in containing the spread of the virus. So that particular colleague of mine, Matt Galati, he was very, very excited, because he said, hey, you know what, this analysis that I was working on and was sitting where it was not that important has now become so critical. There are so many examples now where we can figure out who to contact and stuff like that. So it's become a very critical piece of the fight against the coronavirus. So at the same time as all these innovations and algorithmic innovations were happening, there were several things that also happened. As data sizes grew larger and larger, sometimes the data source was so large that it wouldn't fit on one computer. It would have to be spread multiple nodes, multiple PCs, multiple CPUs, etc. So now when data, even for building a simple predictive model or a regression, is spread across multiple nodes, how do you incorporate and do analysis, simple regression, logistic regression, neural networks, and so on? How do you do all that when the data are distributed? So distributed computing became a very, very important thing for our portfolio. So how do you reinvent some of the algorithms that have been around to deal with distributed data? Then from a business perspective, the need for performance, bigger, faster, better, cheaper, those became very important criteria that all businesses were clamoring for. So how do you do micro-segmentation for customized offers and treatments? And again, you see the number of analysis that goes on for dealing with COVID-19, and the data differs per state, per county, per country, everything. It's so different. So you need to build lots and models for every sub-segment of these populations that you're looking at. So when you've got all these sub-segments that are floating around, you're trying to build custom specific models for all of them, what becomes important? Automation across these thousands of models. So automation in multiple ways. When I talk about automation, let me give you a concrete example. Many of you probably have heard about the Kaggle competitions and other competitions where people are trying to win prizes for getting the best prediction for a particular problem. It doesn't matter what the problem is. So often, they'll have a leaderboard and you keep going up and up on the leaderboard, depending on how much time you have on your hands to see how many models you can run, and so on and so forth. So often the winning entry becomes the one that has the ability to run through multiple models. So by that I mean you run through all kinds of regression techniques, you run through neural networks, you run through gradient boosting methods, you name it, all these different techniques. Within each technique, again, you could have multiple settings. And I believe things like parameter settings, like hyperparameter settings, like when you're building a decision tree, how many levels should you do? When you're doing a neural network, what are the number of levels you should use for your building your neural network? All these different parameters, and running through these different parameters is another challenge. Again, do you have a way to run through these automatic parameters? You could do a simple brute force method, run through the grid of these are all the ways in which the parameters could change, run through it, but then how do you pick it more efficiently, the best model? So automation across thousands of models became very important. So in other words, you're looking for decreasing the latency or improving the performance at every stage of the process. So those were some of the business needs that drove our research. And so it actually, about maybe 5-10 years ago, I would say it was the start of a golden era for artificial intelligence, machine learning, data science, analytics, optimization, whatever name you want to give it, because it was like a trifecta. There was a proliferation of data everywhere, increased computing power, tremendous increases in computing power, and lots of algorithms that researchers were inventing and building, specifically driven by problems that they had to solve. So and this golden era, I think, is still continuing, where you are required to make better business decisions more rapidly in a very, very interconnected world. So automation is the key, automation at every level. And I think that's where some of the innovation happened. So the high performance computing opportunities are everywhere, risk, medical application, network applications. And the challenges with the distributed computing are how do you store the data, how do you access the data, and the algorithmic innovations. And in my talk, I'm talking about some of the algorithmic innovations that we did. I won't talk necessarily about the algorithms, but about the business problem that drove these innovations. So, and at a later point, if there's anything you would like to know more about the details, just drop me an email and I can connect you to the right person or send you the right reference. So increased use of optimization tools was something that I was very excited. And solution techniques that exploit data structures. This is another, I think we've seen that many of you have done advanced courses in optimization, and the decomposition method is something that everybody touts quite a bit, because some of the most complex problems can be solved better if you know that there's a block angular structure, so you end with some few linking constraints. You can find custom solutions for that particular type of structure, which may not work in general, but it is much more efficient. So figuring out what are the solutions techniques that exploit these data. So the opportunities for an analytical innovation, of course, abound plenty. Scalability of existing algorithms, of course. So we had to look at algorithms that have been around for 50, 60 years. Logistic regression has been around for a long time. Even neural networks, which everybody talks about now, have been around for more than 40 or 50 years. So all those algorithms needed to be scaled up so that they were much faster dealing with distributed computing. How do we do all of that? And so my teams, which were used to doing computing on a single machine, a single CPU, they had to learn how to deal with distributed computing. So there are lots of challenges where you need to learn how do you do algorithms where you're not going back and forth between the CPUs. You do a lot of iterations that are within the node and then do some cross computations across the node so that you're minimizing the inter-node connections, etc. So those were some of the learnings that we had to imbibe in them. So the new algorithms were for performance improvement, previously intractable techniques that had been put aside and could not be done. People said that you either don't have enough data or they're computationally intractable. So we were able to bring them back and do some of these. And then wide data as well as long data. A lot of times the predictive models, the logistic regression and just straightforward linear regression, etc., they scale very easily when you have long data. By that I mean many observations with not too many variables. But if you have wide variables where you have lots and lots of features, or features is the term used in computer science, or lots and lots of variables, then it becomes much harder. How do you deal with those? So we had to learn how to do that. Then some of the newer types of data sources, which included high frequency data, streaming data, we had to totally invent some newer algorithms. So I've got a couple of examples here, like in statistics and data mining and machine learning. Support vector machines, that's a very classic and machine learning technique, which gets used quite a bit. And that leads to large quadratic optimization problems. So recognizing that you can use a quadratic optimization solver and then use some tricks within that, those were some of the innovations that had to happen. Quantile regression, this is one of those techniques that was kind of put on the back burner. So when people study about statistics in the statistics courses, when you study about simple linear regression, you're usually regressing around the mean. But when you're trying to do regression along the quantiles, and especially at the upper and lower quantiles, and even the deciles maybe, you don't have enough data. But now with the proliferation of data, you do have data, but being able to use some kind of some new techniques to do that led to some large linear optimization implementation with interior point methods. Deep learning uses stochastic gradient methods. Many of the text analytics algorithms also use stochastic gradient methods, etc. And reinforcement learning, which you hear about a lot in the machine learning area, is nothing but partially observable Markov decision processes. So another theme that I talk about often is that we, from the OR background, we use a certain language for certain algorithms, certain methods that we've used. In the machine learning and statistical communities, they use a different language. So often when you're trying to do interdisciplinary collaboration, is just trying to find that common language and trying to figure out how do we learn from each other, etc. So I talked about automation.
Dr. Kulkarni,
Sure.
sorry, I have a question. I
Yeah.
was sort of related to the two things you mentioned earlier.
Yeah.
So this thing about the velocity, variety, and this thing. So by velocity, do you mean like how frequently the data is collected?
Yeah.
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 So, okay.
Yeah.
So in that case, is that sort of relates also to this point about wide versus long data? Is it right to think that like long data is like high velocity in some sense, like a lot of samples, and then wide data is like variety?
So not quite. When I talk about velocity here I'm talking about, it's mostly like when you're trying to do streaming data, when you're trying to do sensor reading, like, when you're looking at manufacturing, for example, and you've got an assembly line that's going, and you're trying to capture data, like, which is coming very fast, because you could have long data which is actually has been collected over time, but when the data is actually coming very fast, and you're trying to make decisions at the point of time, for instance, you might say, okay, it's especially when you're manufacturing something like chips, like the computer chips and the chips that go into our phone, etc. If the if the assembly line stops, or if it's continuing to go and you've started getting defective chips, it's the standard quality control problem where you're trying to stop the process once it goes awry, right? But when you're trying to manufacture things which are so expensive and you're going to lose so much money by allowing them to go, you want to be able to capture data as and when each chip is going through, and it might be going through very fast, or when, so things like that. So it's actually how fast the data are coming at you, right? So that's what I mean by velocity. Thanks for asking that question.
Thank you.
Yeah, sure. So automation then, would be how do you automate all these different processes when you're either trying to run multiple models or you're trying to do automatically pick the best parameters for a particular model. So we call that auto tuning, where basically you're trying to say, here is the range of parameters that are possible, run through this. And in this particular case, a brute search or something like that might be a way to do when you have very, very fast computers. But if you want speed is of essence, you might want to find some new heuristics. So here is where some of the discrete optimization techniques or derivative-free optimization techniques came into use. We used some genetic algorithms to try and traverse the space so that you didn't have to compute at every combination of the parameters, but you could go very quickly through that. And so that's that kind of technique that a lot of software products now have for predictive modeling is known as auto tuning. How do you automatically tune that? Microsegmentation is when you have the ability to run lots of models. You can, of course, get customized models for every little segment that you're interested in. Feature engineering. This is often the case where you start ending up with lots of wide data, because when you're using statistical techniques, commonly people say, okay, I'm going to build this model using these variables, but maybe looking at the graph, it looks more like an exponential curve. So maybe we should use a log transformation, or we should use some other transformation. So transforming variables is an age-old technique that statisticians have used quite often. But now, with so many different variables that are coming into the picture, people don't have time to figure out which variables should I actually put into the model. So they end up having lots of variables, and then they cleverly choose build new variables by combining them. And so that's called feature engineering. So basically transformation and building new variables is what computer scientists call feature engineering. So again, the ability to build multiple models faster and automatically, that's where the feature engineering comes into play. So I talked about the local search optimization, where it's an intelligent search in the parameter space to tune the models, finding the best model across different modeling approaches, incorporating different criteria into the model selection, and the ability to use black box optimization methods that can extend the scope of applications. So basically, when you don't have a closed form representation of your objective of your functions, then a black box optimization method can be used, and you can use some of these local search optimization techniques to get a better model, to tune your model. With high frequency data, where data are coming very fast and very quickly and in different forms, some of these examples are when you're trying to take continuous measurement of data. So the examples are temperatures, pressures, velocity, operating status, etc. And event data, where intermittent event occurrences are happening, like when does the plant shut down, when does the machine shut down, etc. What is the idle time, repair time, etc. So in order for us to be able to solve these, we had to invent some new principal components analysis types of things, where we call that the robust principal component analysis. And it's used quite often where you're trying to separate background data from foreground data. So here is a cool video. I hope you can see the movement on this video. So the original video shows a place where you're trying to, a lobby in a hotel or an airport or whatever it may be, where you're trying to monitor what's going on to figure out if there is some activity that is nefarious or problematic. So from the original video, you need the ability to separate the foreground, which is the people moving, from the background. So the third picture is actually the background, which is supposed to be stationary. So people, this is a technique that is used in surveillance to be able to do surveillance on lots and lots of videos very quickly. So for instance, if somebody is watching this and finds that the background, suddenly there is a backpack that has shown up in the background because that's not moving, but everybody else is moving, You say, hey, maybe that backpack shouldn't be there because somebody who was moving left it there and went away. So you get the picture. So using robust principal component analysis, we were able to do analysis of this kind for several problems. And recently, we use this technique. I say we, I still refer to SAS as we, okay, even though I retired almost a couple of years ago. So this is a very interesting project, which was for monitoring beehive health with streaming data. So, we all know that bees play an important role in agriculture, and having bees that are able to pollinate, cross-pollinate is very important for how well the produce is growing and so on. So not having healthy bees is a big problem for agriculture. So how do you ensure that you have healthy beehives in the vicinity or in your farm or wherever you are growing bees to support your agricultural crops? So you're trying, they were measuring the weight of the hive, temperature inside and outside the hive, the humidity, the acoustics of the buzzing inside the hive, and flight activity in and around the hive. So some of this are just numeric measures like the weight and the height and the humidity. They are numbers that you capture, but the buzzing of the bee is an audiophile. So you have a sensor that is installed right near there, which continuously streams the sound from the beehive and also captures video images of bees going in and out, whether there is activity. So if you suddenly find that the activity is not what it should be, that it has suddenly slowed down, or if you have two hives sitting next to each other and you find suddenly that one of the hives is increased in activity, it might mean that the queen bee of this first hive has actually flown away and maybe gone to this new hive or gone away, in which case this first hive is doomed to suffer. So these are the types of things that you're trying to look at and trying to get. So I've included some links in here, and there is one which is actually a nice description of this particular project. So the audio files, again, taking the audio files, separating the background noise from the foreground and video files, all of that, it talks about how they did that, and there is a more detailed paper about how they did that as well, which is the PDF link that I've included here. So one of the questions you might ask is, what is the big deal here? Why is it such a big deal that we are able to do this? Were people not doing this all the time? But of course, then people would have to go in and actually measure and have some manual measurements or collect all of that, which again disturbs the hives. So here you can just leave the instruments there, collecting the data and sending the information, streaming it back to the IoT. IoT is the Internet of Things server back on campus, where they can measure and do this analysis and figure out, okay, this beehive is in trouble and so on. So the same type of separation that I talked about for the video surveillance for video data is used for the audio data as well. So listen to some of the video, the audio file. It's very interesting. A new beehive, queen bee comes into the hive, you actually hear a real piping sound, which is very, very interesting. So it's fascinating. So bees are fascinating. I wouldn't want to be stung by one, but this particular project I thought was an interesting example of working with streaming data and automated analysis. I talked about the manufacturing example already, where you've got an assembly line, and the key is you want to stop the assembly line as soon as the first chip, or very soon after the first chip is defective. So detecting defects automatically in wafers as they move through the system. So again, the streaming data goes to a central system where it's measuring. So the key is, of course, you need to have the training that has been done ahead of time to say, to figure out how can you detect a defect, what are the defects that it's known to measure, and using all that, how do you keep monitoring it so that when the defective chip starts coming out, you can stop it right away. Another very interesting example of the IoT data is for trains. So more and more regulations are coming into play where trains that are used for transporting chemicals or has other hazardous material. So if there is a problem on the train and it's likely to have an accident and fall off the tracks or something else were to go wrong, the chemical spill or the hazardous spill could be very, very disastrous. So we need to have some mechanics sitting right on the train, and we call that being able to do a positive train control, where on the train itself you have some mechanics which is looking at, have some sensors, sorry, which is looking at lots of data that is coming out from the operation of the engine. And as soon as something goes wrong, there should be a control right then and there to stop the train. There may not even be enough time for that data to go back to the central location and somebody say, okay, now we need to stop the train. So this is the type of thing where we say you're putting some of the analytics results or the training model right at the sensors on the train to stop it if there is a problem. So that's another really cool example of using streaming data and being able to do an analytics right at the edge. So we used to think about analytics at, all of them require algorithms. But when you're using the algorithms with data that has been collected over time and building the predictive model or models that are going to help you predict the future, we call that at-rest analytics, because that's what you're using for your training data and building it. In-motion analytics would be an example of the manufacturing example, for instance, where you're noticing that there is some problem and you can have somebody at the control saying, okay, we can stop it. The edge analytics is where you have some remote thing going on, like the train that's running automatically, but then right at the train itself, there are some sensors which will say that here it's monitoring it, and if there is some problem, you stop it. So at-rest analytics, in motion, and edge analytics, that is known as the analytics ecosystem. So that's what we refer to as the analytics ecosystem. So this data that exists that you're using to build models and then discover any patterns in the models or what your future predictions could be, etc. But then deploying it in practice. This is the cycle that is very important. And oftentimes when we have people graduating with advanced degrees in operations research or statistics or any of the analytical areas, we focus a lot on the discovery part. We focus a lot on the building of the models and the algorithms. We don't spend too much time on the data issues that might be happening, nor on the deployment. So deployment is a very, very key part of what we need to be focused on or take into consideration. And the reason I mention that is because sometimes your best and the bestest algorithm, if I may use that word, may be something that's very hard to put into practice or keep going. So it might be that a simpler algorithm, a simpler method actually works better for the deployment. So taking that into consideration is very, very important. And so that's a lesson that many of our students, as they came in and started working at SAS, even when they are in R&D, they still are trying to do the best algorithm, find the most, the minimum gap for your optimality and so on and so forth. But once they start going to customers and actually implementing what they're trying to do, that's when they realize that you have to pay more attention to other things as well. So is analytic innovation enough? So some of the critical barriers to success are in data, process, acceptability, and talent. So, am I covering things reasonably? If there's any question, this is on the first part. I'll come to the barriers to success now. Okay. So, do you have the right data? And an example that I like to use quite often is facial recognition. facial recognition is something that we all hear about, and it's one of the common uses of machine learning algorithms, predictive models, etc. And it's very important because it's used for all kinds of decisions, right? So do you have the right training data? And I was talking earlier during my discussions, and that is a problem that we face quite often, because if your training data is not rich enough, is not full enough, then you will make mistakes. Like, one of my friends, she said, she's a Caucasian, and she said she lived in China for a while, and she recognized that she could probably get away with robbing the bank in China because they did not have anything that would recognize her, because their training data did not include Caucasians. And I guess you can say the same story from any different perspective. So I've included a link here about a young woman called Joy. She's a Ghanaian American woman, and this is a TED Talk, which is an awesome TED Talk, where she was actually working on in the MIT labs on some facial recognition software, and she was perplexed because she's of course Black, and she was perplexed because the software didn't recognize her as a human being even. They didn't, and so, and that's because the training data was not rich enough. It did not have enough people from different colors, different ethnic backgrounds. And so over time, I think some of the work that she did actually caused some of the big companies like Google and Facebook also to take that into consideration and make sure that they had a richer set of training data that they could use. So that's a paper that is really worth a presentation that's worth looking at. And so she established an algorithmic justice league to make sure that algorithmic bias doesn't happen as much. Do you have the right process? This is where some of the deployment that I talked about, or even implementing a particular method. So marketing optimization or offer optimization was a solution that we worked on with lots of innovative heuristics for a very, very, very large mixed integer problem, because you could have thousands and thousands of integer variables here where you're trying to figure out which offer to make to which customer through which channel for what product. So you can imagine if you've got thousands of customers or even a dozen offers and about 5 or 6 channels, it can explode the number of integer variables. So we had an excellent heuristic that incorporated a lot of the key optimization techniques as part of that. But when we went to implement it, when we talked to customers, there was a big problem, because the campaign managers, the CEO said, hey, we've got this cool marketing optimization solution now. So all of you campaign managers, rather than dealing with individual campaigns, let's put them all together and we'll have a global optimum and find the best way to do this. But sometimes the optimization engine might say campaign manager A does not actually get any campaigns in this particular cycle because that's not contributing to the optimum. So now how do you explain that to the campaign manager? He says, just give me my money. I'll go do my campaign. I'll get some profits out of that. So in order to do that, the CEO or whoever has put this solution in place needs to be able to explain or even change some incentives so that all the campaign managers agreed that a global optimum is good for this reason, and here is how you'll be compensated if some particular campaign goes without any offers for your particular region. So this is where an executive support for procedural are needed. So make sure when you're going into implementing a product or a project that you have that level of support so that your solution can get approved. Do you have acceptable results? More and more people are asking for why. Why did I not get this offer? Why did my neighbor who lives in the same type of house and all of that, why did his loan get approved, but mine did not? So how do you explain that? What are the reasons? So this is one of the reasons why, even though we've got so many different machine learning algorithms, decision trees are, because decision trees easily tell you this is why this branch didn't go, this is why this didn't go, etc. And you can tell what the final results are in the optimal model. So interpretability is important for the modeler, it's important for the consumer, and it's important for the policymakers. So for all of these, how do you make sure that your decisions are interpretable? So especially for some of these very complex algorithms like neural networks and deep learning net models and so on, there's a lot of research going on in how do you make things more interpretable. And this is where what the policy regulators need to look at is what are the ethics involved. So you can have an AI solution that comes in and tells you this is the best way to do a particular thing, but is it fair, and does it provide equitable incomes? Is it excluding bias, or is it increasing bias? Does it make the humans feel left out or something? Do you need to put something else in place? What is the role on existing employees and all of that? So these are some of the things which are also important. So when we get involved in any of this machine learning, any analytics project, these are some things. The more automation you bring into it, you still need to make sure that there is a human acceptance of the results. How do you explain it? And often in projects that we've done, it's been trying to show that something works better than before, or trying to find some simple example that can help them understand and gain your trust, and then move forward. But ethics in AI is an area that hasn't been done. There hasn't been much work done in, and many of the newer institutions that have been set up with a lot of money going into it, like an Institute of Data Science, etc., they're recognizing the importance of the sociological and legal aspects of it. So the data science umbrella often includes people who are experienced in the ethics and the legal aspects as well, so that the algorithms that are being propounded don't violate any of these rules. Do we have the right people? So analytics literacy at all levels, I believe, is very important. So you might have being a core ORIE department, many of you are studying how to create analytical models, invent new algorithms, exploit analytic, and so on. So that's the first sub-bullet under the analytical expertise. So if you are pursuing a PhD, you're learning how to build new algorithms, you're learning how to create new models. So that's of course needed for the core R&D work that needs to happen for solving new types of problems. But you also need people who can exploit the analytical tools and make sense of it. So even though many of the newer software packages have automation built into it, they need to have the ability for people to exploit them reasonable way, and the people using them need to have a good way of using them and use them correctly. So analytical expertise can be at two different levels. Leaders of research groups also, they might have lots of PhDs and master's students under them working, but they need to understand what they're working on. So that was one of the wonderful things that I felt about working at SAS, because our CEO was really, he understood the analytics at every level. And so it was easy for him to see what was and so on. Then of course for business leaders, so they need to also understand. So you need to have analytics champions, analytical modelers, analytical experts, analytics consumers, and analytics enablers. So by that I mean, when you're trying to build data sets that are going to go into your analysis, you usually have database stewards and database who are working with you. They need to understand what is the data being used for, what do they need from it, and how are they providing it. So these are all different ways in which you can increase literacy at all these levels. And for a whole project to be successful, you actually need every one of this. So building analytics team for success, I've given a link for a paper I wrote earlier this year. And that one talks about some of these analytics literacy and what's important for success. So summing up everything, Automated data-driven decision-making is something that all of us have been striving for, taking data and getting value out of that. So it essentially requires us to learn with new sources, new types of data, exploit new analytics infrastructure for the large data, and explore and implement new algorithms, and educate and train your workforce. So those are some of the highlights of what I covered. And here's my email address for anyone to reach out to me if they want to explore any of these points further. Thank you.
Thank you, Dr. Kulkarni, for a very thoughtful thing. I guess it's hard for us to convey feedback.
That's okay.
uh, um, yeah, so I'll open the floor for any questions if someone has.
I saw you had, you mentioned partially observable MDPs. Can you give examples of what types of problems you solve using POMDPs?
Oh, you got me there. So those are some of the it's all, most of them come in when you're trying to do deep learning techniques and trying to in text analytics, computer vision, and audio visual data, and so on. So I don't know too much about the details because I had a team which worked on that, but I can send you more information about that from them.
Thanks.
I can give an example from industry, actually. So when I was working at Target as a postdoc, I actually used POMDPs to model clearance pricing. The partially observable part is that you didn't fully know customer demand. So that was an example from industry of a POMDP.
Sure. Thanks for mentioning that, because that reminded me, that's similar to the revenue management problem we were doing for hotels and in the hospitality industry, where, when you're looking at trying hotel demand, the demand is, there's a lot of unforeseen demand, because when the rooms are full, you don't know what the demand could have been, right? So that's another example. Thanks for.
Yes, I guess the reason I ask is I know there's any number of papers, I guess, where we model various OM problems, such as pricing, for instance, using POMDPs. So I was just curious how realistic this is from an implementation standpoint. So I guess what I'm hearing is it is realistic, at least somewhat realistic.
Yeah, actually, especially in I know about the revenue management thing, because my team worked with the revenue management and pricing optimization solution from Ideas. Actually, Ideas is in Minnesota. SAS acquired that company, and we built some new engines for that, and dealing with unseen demand, and how do you account for that in your pricing and your estimation of demand was a very key part of it. So drop me a note, and I'd be glad to connect you with the leader of that group, because he'd be able to give you more insight or send you some papers on that.
Yeah, thank you.
Any other questions? So I have a question that is sort of related. So in some sense, so I have seen like other instances where like people talk about interpretable, like machine learning and AI, and most of these settings I observed that you end up using like some decision trees or some random forests and things like that. So are there like other, I'm not familiar with this, but like are there other sort of techniques that are considered more interpretable than some
So one of the simplest approaches that people have used is when there is, so let's say you've used a gradient boosting method or some of these harder to comprehend or interpret methods. So take that, so what what's been considered to be what's the result, what's the response, and so on and so forth, and use that and post facto build a decision tree out of it, with the results from the model, and then see if that can help people understand better. But then there are other techniques. I believe there's one called Lime. I forget what the expansion is, and I can send that to you too, where there's actually some advanced techniques where people use to do that, and there is also a video that's available on our site, which I can send you a link to that.
Thank you.
So I have a question. So one of the things you talked about was ethics and, optimization or AI. And I feel like this is probably quite important, but also difficult. I mean, most of the people who are working on these systems have no training in ethics. And I mean, some of these things, like we've talked about, there's kind of, overlap between the machine learning community and operations research a little bit, even though there's different languages, but there's like no overlap between ethical philosophers and operations research. So, how do we, and in terms of research interests, it's hard to make that connect. So what's the way to get the ethics into the algorithms?
Good question. I guess first and foremost, there needs to be a greater recognition by people working on the algorithms that this is an important consideration. And, I think it's something that I have not seen happen, but you increase the collaboration between the people working on the algorithms and these other fields, right? And I think the data science institutes that are being set up now, like the one in MIT and UVA, there's been a huge investment in all of that. I think they do include these departments and subgroups as part of the entity, right? So at least now there is recognition that we need to take consideration. We need to make sure that there is a greater discussion between them, and so it's an area that not much work has been done. I agree, and but it's important, and there, raising the recognition that it's, we see lots of stories in the public media where people can disparage AI algorithms, saying that it could take decisions which are so harmful, blah blah blah. But then how do you change or modify the results so that there is some ethical component in it? At this moment, I guess, making sure that you have humans in the loop. You cannot take humans out of the loop, right? Automation is well and good, but you cannot take humans out of the loop. They have to be involved in these decisions. But how do you get people to understand it more? Is that something that we should include in the curriculum to think about? I think those are all questions, especially with so much of discussion going on about racial justice and discrimination and all of that. Just simple things like facial recognition, right? The example that I mentioned, facial recognition. So that particular I think I mentioned the TED Talk by Joy, and some of the work that she has done has at least raised awareness of some of that. And this Algorithmic Justice League was established to ensure that people pay attention to algorithmic bias.
Okay. Any other questions? So if not, let's thank the speaker again.
Thank you.
And just to remind you, so we'll end the official part of the seminar now so the recording can stop.